Hello and welcome back to Teaching C My Way, and we're now on episode 3 in the series, and we're finally going to get on to doing something interesting. So in episode 1 we talked about why I think C is important, and in episode 2 we talked about the most basic C program in existence, but I realise now that I actually told a slight lie in episode 2. I told you that the most simple C program is the Hello World example, whereas in reality this here is quite possibly the most simple C program in existence, because this is the minimum, or actually this is the minimum that qualifies as a valid C binary. And if we compile this and run the produced executable, we can see that it simply runs and exits immediately. This is a valid binary, it's a valid C program, but it does absolutely nothing, and this is the absolute bare minimum that's required to produce a working program. However, today I'd like to dig deeper into what this actually means here. It might look insignificant, but these two braces here are some of the most important things in C about how our programs actually work, because this is a scope. And today we're going to be talking about variables, of which scope is a very, very pertinent subject. So, what we've done here is we've declared a function, and a function we can go into more depth into later, but for now I want us to understand a function as simply being a fragment of code. It is simply a section of your program's source code, and therefore a section of the binary in the final file, which is going to execute together. It's a bunch of instructions that will work in a sequence. And so the main function of your program is important, as it tells C where you want your program to start. We don't place any code outside of functions in C. No code can ever be executed that's not in a scope like this. And the reason for that is because of how scopes and the stack work. And to understand that, we're going to take a dive into variables. So, before we get into variables, though, I'd like to reiterate on a golden rule, and I can't remember whether I mentioned this last episode, but I'm going to introduce it as though it's new now. And I'm going to write it in the source code here, like a professional programmer. Identifiers, and we're going to just quickly define an identifier, and that's the human readable name of something in the program. So your program's made up of a lot of objects. They could be functions or they could be variables, and an identifier is the human readable name, but an identifier is just a name for a location in memory. It is just a human readable tag that we have attached to a memory address that the linker, see last episode, that the linker is going to attach a memory address for us to it once it does the final translation into the binary. And so this main here, you could effectively substitute this for, I don't know, 0xFFFFF7C or something, and it would make sense. This is what this will actually mean in the end. So an identifier is just a location in memory. So whereas a function is the location in memory of a fragment of code, a variable is the location in memory of a piece of data. And so in C, a piece of data is made up of two key parts. It's made up of the type and the identifier. So the type defines, well, the type of the data. It defines what's allowed to be stored here, but more crucially than that, because if we think, what actually is data inside all computers? Well, memory is just a sequence of binary numbers, so all data is really just a number under the hood. So what actually is it then? Well, types in C are actually the size of the data, and we'll talk about that a bit more in a moment. And the identifier, as we saw a minute ago, is the name. So when we create a variable, we're telling C that we want space in our final binary at some location to store a piece of data at this place with this human readable name, and it's going to have this certain size. And so the compiler, not the linker mind, the compiler needs to know the size, and it needs to know the identifier that has that linked size. So in C, in order to get a piece of this memory, we first had to declare a variable. And when we talk about a variable declaration, I want you to keep that in mind for later. We're declaring to the compiler, we want this variable to exist. We're telling you as an instruction this will exist. So, now that we understand some of the basic theory behind a variable, it's effectively just a name and a size for a location in the memory, and instructions on how it can be used further. We now need to take a look at how variables can actually be used. So, in C, the most basic form of a variable is simply a variable inside of a function like this, declared as a declaration. So remember in C, statements, and this is a declaration statement. We're stating to the compiler a statement of intent. We want this variable to exist. We're telling the compiler that this int x now exists, and we can now do things like return x. We can now reference x. So x here now exists at some place in memory. And to understand where it's going to exist, because remember we need some place to store everything, we need to understand this scope. So a new scope in C at all times creates a new stack frame. And so a stack we can imagine as a literal stack of objects. So the way that we store a stack is we have a base, and we can imagine this line here as the base. And so every time we add a new object, for instance, let's just do an analogy of a shopping list. So whenever we're creating a stack of things, we add something new onto the top. So when we create a new variable, we're adding something new onto the top. So let's push, I don't know, milk. So let's say suddenly now that we have bought some eggs. So we push our eggs onto the top of the stack. And then maybe we buy pizza, and maybe we buy beef as well, or something. But suddenly we now realise that we don't really like beef very much, so we need to get rid of it. Well, first, we just pop it off the top of the stack, and that's really easy. But then what happens if we decide that we don't want milk anymore? Well, we have a problem, because if we just get rid of the milk, everything else is still here, because remember, this is computer memory. Things aren't just going to shift around on their own. And so, in computer science, a stack in memory can only ever have the last object of it removed. You're allowed to change the values anywhere along here, but you can only ever remove things from the end, never from the beginning. A queue is the opposite way around. You can only remove things from the beginning but not the end, but that's irrelevant for now. When you create variables inside of a function like this, these are called stack-scoped variables. And this means that the memory that you have has been created at runtime, and that means it's created when the binary runs. The C language is going to allocate it for us when the binary runs, and it's going to allocate it for us when we enter this function. And that's what this brace means here. It means we're creating a new scope and a new stack. The new stack is known as a stack frame. So when you hear about a stack frame, unwinding stack frames, or stepping through stack frames, what we really mean is a new scope where all of these new variables are being allocated, all of this new memory. And so this memory doesn't just come from nowhere. It's not being created, conjured out of nowhere. It's being allocated by moving around one of these stack data structures. To a certain extent, the variables which are our arguments as well, which we'll meet in the functions episode later on as well, are also on the stack. But something that's extremely important to realise about the stack, or there are two things that are very important for us to realise about the stack. First of all, it lasts the lifetime of the function and cannot be seen outside the function. So whenever we create a variable inside of this function, if we have any other functions, none of them can see this variable, and that will make a lot more sense later on once we meet functions properly. But this variable in here cannot be seen by any code that's outside of these two braces. And if we had another function, void func, and remember here we're creating another stack frame, and then we call this function down here. If we create an int x, these two x's are completely separate from each other because they're inside different frames, and the memory that's created is completely different. It's completely separate. So the second thing to realize is that stack memory is limited. you can't create infinite amounts of stack memory because that will create something called a stack overflow. You can't simply keep creating more and more memory and you will eventually run out of it. And you'll run out of it much, much quicker than you think. And once we meet the heap later on and dynamic memory allocation, we will understand different reasons why this is the case. And the final limitation that I'm not going to write down is, though, that we need to know the size of the data at the time that we're creating the binary. When I said that it's created at runtime, the memory on the stack, what I really mean is that the instructions for allocating the memory will run at runtime. There isn't space allocated in the binary that will hold this variable. And this memory being created and destroyed at runtime is the reason why nowhere else can see this data, because once this function exits, the stack that it was using will be destroyed and reused for something else. The memory will be freed, in other words. And so this means that this variable is not safe to use once that we've returned. And we'll talk about how that can be a bug again in the functions and pointers episodes. So we talked a lot about the mechanics of the variable here, but what does this variable actually do? Well, as we said a minute ago, this variable is simply a pointer for a location in memory. You can think of it as a little box that you can either place something in or get something out of. And so we can set the variable of a function. And so just like in mathematics, when we want to set the value of a variable, we just say the name of the variable and set it equal to something. So the type of this variable here, remember this denotes the size and the things it can be used for, is an int. And if you've ever done mathematics before, which I hope you would have, you'd realise an int is an integer. And so what we've done here is we've said this variable x is now equal to 1, 2, 3, 4. We can then set it again. We can set it to another value. So at this point in the program it's equal to 1, 2, 3, 4. And at this point in the program here, it's equal to 4, 3, 2, 1. And so the value has been changed, because variables can have their value changed at any time. You can create more than one variable as well. So here we've created two variables. This can actually be shortened to int x, comma y, but let's keep it simple for now, and let's say x equals 1, 2, 3, 4. And so x, at this point in the program, on line 11 here, is equal to 1, 2, 3, 4. And then on line 12, let's say that y is equal to x. Now this is interesting. What's happened here? Well, what's happened here is we've set the value of x to 1, 2, 3, 4, and then we have set the value of y to x. And just like in mathematics, when we do that, what we're saying is the value of y is equal to the value of x. And it's important to note as well that these are still completely separate variables. If we then set the value of x equal to 5, 6, 7, 8, the value of y is still 1, 2, 3, 4, because the value of y was set up here and it has not been set again to the value of x. The value of x is read at this point in the program, and it's stored into y as though a little box. The value of x is, in other words, copied out of the value. The value of y is copied out of the value of x. And so when the value of x is overwritten, the value of y is unchanged. And we can set y to some other value, anything that we want, and this will overflow, but it doesn't matter for now. Let's just make it smaller to get the warning to go away, but this will completely not affect x at all. So I mentioned as well that we have many different types of data, and so far we've only met one of the most basic forms of data possible, and that's the int. The int is a medium-sized integer. It's a whole number. It's not allowed to have decimals. We can't say, for instance, that x is equal to 3.5. We will get a conversion warning that will tell us that the value will be changed to 3. Because C, when we set an integer to a floating point, will just chop the floating point off for us. And this can lead to some nasty bugs if you're not careful. So how do we store floating point numbers then? or how do we store numbers with a decimal, I should say. Floating point's a computing term, I realise. But the way that we do that is we store things as a float or as a double. A float and a double are functionally the same, but a double can store a wider range of numbers. It's larger in size, as we saw up here. So let's just use a float for now. And so if we set x to, I don't know, 3.14, like the first values of pi, we can see that we don't get any warnings. We are simply setting this to the value 3.14. And under the hood, this uses floating point mathematics and IEEE 754, it's called, the floating point number standard. But all you need to really know is that C and the processor will handle these floating point numbers and all of the kind of rounding and all of that garbage stuff for you. So far we've met how to do floating point numbers, which are decimals and whole integers. But there are some other types that should be mentioned as well, and one of the more useful types of these is the char. The char, which is short for character. Just put a little note here, and so we can say char C equals, and then the value of a character. And so in C, when we're storing the value of any literal letter, we put it in single quotes. So what's actually going on here is that C is going to convert this character to an ASCII number under the hood. So we can actually write this capital A is equals hex 41, and this is the exact same as this. These are the exact same piece of code. This does the exact same thing. But the compiler does this for convenience, so we don't have to memorize an ASCII table. But the single quotes are very important. This is an invalid definition. You cannot initialize a char with a double quotes, because this is actually a string, and we'll meet these in the pointers episode again. But all you need to know is that a char is a single character. Now I realise at this point as well that I've been talking about variables as well as if you have to declare them and then on another line you have to put their value in. But there's also something as well called a shorthand declaration, and this is where you put the value that's the initial value, the value that the variable will start off with, right next to the place that you've declared the variable. So we could do this here as well. And so these are now two separate pieces of data initialized. And we can still overwrite the value, we can set it to whatever we want later on, but it will start out with the value after the equals sign here. Another piece of another data type that you will probably find explicitly very useful is the long data type. So I mentioned a minute ago that floats and doubles are functionally equivalent, but a double can store a wider range of values than a float. Now, a int and a long are exactly the same in that a long is longer in memory than an int. It could store a wider range of values than an int can. Because an int is 32 bits, a long is guaranteed to be at least more than 32 bits. On 64-bit platforms it's 64-bit, on 32-bit I don't really know what happens, I don't use 32-bit platforms. But you see, the C language will guarantee to you that this is larger than this. And before we finish talking about data types for now, there's another important attribute of these types that we should talk about. So when I said that the type of a variable denotes the size, something I also forgot to mention actually is there's also something called attributes that go along with it, and these are about the properties of the variable. So there's one that's like const, and then there's unsigned, and for instance static, and there are a few of these. There are a few different of these keywords in the C language that tell us different properties about a variable. But in C, all numbers by default are allowed to be negative. This can be negative, you know, it can be negative and very large, it can be negative or very small, and floats can also be negative. This is negative pi. We're perfectly well, this should be Z. Floats can also be negative, but what happens if we don't want our number to be able to be negative? What happens if we explicitly know that this variable will never have any valid case where it will store a negative number. Well, in that case, we can tell the C language, do not include information in this variable which says whether it's positive or negative. And when you do this, you actually give yourself a wider range of numbers that you're allowed to store, because an extra bit inside of the variable that's being stored, inside of the binary that's being stored internally, I'm going to draw a diagram to explain this. Each number is stored, 2, 3, 4, 5, 6, 7, 8, as a sequence of zeros and ones. So for instance, the number 1 is stored like this, the number 2 is stored like this, the number 4 is stored like this, so the number 6 is stored like this. And this is called binary 2's complement, because what is actually happening is this final bit at the end here is called the signature bit, or the sign bit, and this tells us whether the number is positive or negative. So this here is the number 1, this here is the number -1. Very, very simple. But if we don't want our number to be able to be negative, all the C language does is says, okay, this last bit here, instead of being the sign bit, this is just another number bit. So this here is not -1 or -0 or whatever. Instead, this is some very large positive number. So how do we get C to do that for us? Well, all we have to do is to put unsigned before the name of our variable. And so if we want an integer that's not allowed to store negative numbers, we simply do unsigned and then the data type int equals and then 255, for instance. And we need to give it a name, obviously, I just forgot. Let's give it G, whatever. You should always use meaningful variable names. I'm just using sample ones for the moment. It's important to note as well, I don't think you can have an unsigned float, because it's the way that signatures or sign bits are stored in floating point numbers is to do with the exponent, and it doesn't work the way you'd think it does. You can't have unsigned doubles either, but every data type, including chars, actually, which is a funny quirk of the way that C works. You can have unsigned chars, you can have unsigned longs, you can have unsigned everything practically apart from floats. And so all unsigned means is this cannot be negative. So we've met some of the basic data types, and we've met how these are stored inside of the function. And so we've also met the fact that we can deal with data in a C program. But this is not the only way that variables can be created. There are other types of variables. So when I said that these variables are created at runtime on the stack, there's another type of variable which is allocated at the time the program is compiled, and this actually clears out some space in our binary, and it says, as we're compiling the program, we want space in this binary, and we want to be able to use this space for data at the end of the day. And because we know the size at compile time, and we don't have to keep creating it and destroying it in these frames, because it's going to last the lifetime of our application and never get created or destroyed, we can simply create the space once, either at compile time or at startup, and not worry about it again. And these are called either global or file local variables, or translation unit local variables. And these are created by simply declaring a variable. Remember, a declaration just says this is a variable here, and declaring it at the top level of the program, outside of any scope blocks like this. And what this does is, it says, this variable here, we know it exists, and so we're going to get space for it at compile time, and so you can use this variable from any function that you want. But for every function that you go into, it's not a new copy of it in every new function, it's all one variable. They can all write to the exact same place. So if I were to go down here, and if I were to go var equals 1, 2, 3, 4, then up here, the variable of var is now equal to 1, 2, 3, 4. If I were to create another function, void func, and then modify var equals -2, and then call func down here, and that's going to make the code inside of this block run here, then var at line 23 is now equal to -2, even though this is in a different block. So Any variable which is outside of a function is global and can be seen by every function in the entire program. Now it's important to note that when it's in this file like this, you have to do some tricks to get other C files in the same program to see this variable, because the compiler needs to know about it, because it goes through each file at a time in isolation, and that's where things called header files come in that we're going to meet later on. But sometimes you don't want a variable to be able to be seen by every single C file in the program, and we haven't met how to do multiple C files yet, but don't worry, it's very simple actually. But sometimes you don't want them to be able to see it because it's just part of this piece of code. And in that case, you just append static to the beginning of the variable. And that says this variable can only be seen by this C source file. Nobody else can see this, and so it would be like, this obviously won't work, but it would be like if we wrapped a giant pair of braces around this C source file. It's not being created on any stack, it's still being allocated pre-allocated in the binary at compile time, but it can no longer be seen by anybody else. Now the final attribute that I'm going to talk about for now is const. And const is very, very useful, because what const does is it says this variable is constant. Its value cannot change. And variables can be constant either on the stack, let's make this C equals 3, or they can be global, const float pi equals 3.141592, or they can be both static const. And you can do this, you can reference other variables at the global scope still, remember. And this star here means multiply. We're going to meet operators in the next video, I think. So we can create variables that are const. So what this means is, attempting to set the value to anything else results in an error. Type check assign const cannot assign variable C with a const qualified type. And whenever you see qualifiers, it means one of these attributes here. So this is being qualified here. In linguistics, we often talk about a qualified noun, or for instance, an intensifier is a qualifier of an adjective. We say things very big, the very is a qualifier, it intensifies the adjective. In this case, the static and the const are qualifying the float. The static says only in this source file, the const says you're not allowed to change this. The const here tells us that pi is a constant, it will never change. The float tells us it's a floating point number. And so you can see how all of these working together can allow you to handle pretty much every type of data under the sun. Now, we haven't yet talked about how we can actually deal with text, but I mentioned a minute ago that everything under the hood is basically a number, and this is another golden rule of C that I want us to hold in mind, and really a golden rule of computer science in general. Under the hood, everything collapses down to a number. There is no such thing as text in memory in a computer. What's really happening is every character in that text is being translated into ASCII, and if you just Google ASCII, it will give you a good explanation of what's actually going on with ASCII. But everything is just a number under the hood, and so if you're wondering why we're not talking about text yet, or why was he talking about the character, the char being turned const char, I don't know, ch equals capital A. Why was he talking about it turning into a number? Well, because this here is actually just a number that the C compiler knows how to look up in a little table it has in its own program. So hopefully now we should understand a little bit more about how data in C is actually handled. And so I want to do a quick summary like we did last episode, and then I'm going to actually give a few exercises that we could do before we attempt the next episode. So, just to summarize, a variable is created by giving it a type and then giving it a name. And so the type determines what the variable can be used for, and it determines its size. The name is simply the identifier, and this is the human readable name attached to its memory address for convenience. A variable which is created inside a block like this is called a stack scoped variable. You can have a limited number of these that you'll practically never reach if you're doing everything right, but you can have a limited number of these, and they are destroyed when the function returns, or you can create them globally or file scoped like this, and they are allocated at compile time and can be seen and changed by every function. A constant variable cannot have its value changed, and a static variable cannot be seen outside of this source file. And a integer is a whole number. Something that's unsigned cannot be negative, or I should mention as well that something that's signed is explicitly can be negative. But you don't need to do this because this is equivalent to this. It's exactly the same. The C will implicitly insert signed here for you. But I should just mention this just for completeness. A float is a floating point number, and a double is a floating point number that can store extra digits, basically. And you are allowed constant variables on the stack as well, and a char is a single character. We haven't met how to store multiple characters yet. You can do that, don't panic. You don't have to write out your strings like int character 1 equals and then whatever. No, you don't have to do that. There is a way to do this that's less tedious because C is smarter than we are. Next golden rule we should write down: C is smarter than you, trust it. Okay, so I'm going to do something different this time, actually, and I'm going to give an exercise for us to take away and to attempt to do at home. So, can you remember, first of all, what the very basic layout of a C program was that we've been using for this whole time that the compiler will accept? And if you can, it's a function that returns an int, and it's called main, and it accepts two parameters, int argc and char star star argv. This is char pointer pointer. But you can omit these arguments entirely, and it doesn't matter. For now, you can do that. Just all you need is a function, int main, and the two curly braces. So, these are the exercises that I want you to try to see if you understand variables properly. So, I want you to create a variable x and store 79 in it. Then, I want you to create a variable x2 and store the value of x in x2. Then I want you to change the value of x, not x2, to any value you want. You can change it to anything you want. I don't really care. 69, 420, something funny like that, preferably. Then I want you to create a variable which can store pi with a suitable type. I should say about this as well, this should be of a suitable type. Then I want you to create a variable which is storing the letter x. Right, finally, I want you to create a variable, and I should mention actually these should all be done on the stack. Create a global variable which can store a single character, and then I want you to create a stack variable which can store any non-negative integer. Then, final one, I promise, I want you to create a global variable called myConstant, which stores a math constant of your choice. if you're watching this, there's a realistic chance that you have a favourite math constant, so all of you nerdy people, get on the internet and go and find up some rainbow table of like digits of the golden ratio, or like 22/7 or whatever, and type out as many digits as you can into the floating point number. And I'd like to see what qualifiers you choose to put on 8 here. Should be interesting. And when you think that you're comfortable with doing all of that, have a play around and see how many variables you can create, see what you can do with them, and just have a mess around with creating them. And don't forget as well, after you've done all of this, don't forget to compile your work, simple.c, and see what happens. For now, it will be absolutely nothing, but it's quite cool to remember that under the hood, when you type int x here, do tcc simple.c, and then run a.out, that under the hood, all of what I was just talking about is really happening on your computer. You have just controlled directly your computer exactly what is happening. And this is the beauty of why I like understanding things perfectly. I'm going to give one final problem, and this is a more difficult one intentionally, that don't feel bad if you can't address it, obviously. So, Alice is trying to store a very large number. She uses a declaration like this: int x equals. The compiler gives an overflow warning. What should she change? What should she change about the declaration? And I'm going to give a hint. Think about qualifiers and types rather than anything else. Right. So that concludes this episode on variables for teaching C my way. And so hopefully at the end of this you should understand what a variable actually is, as in what it does in memory. You should understand at least the basic types in C and how the C type system works. And you should understand some basic qualifiers, and hopefully have a basic understanding of where the memory that backs these variables is actually coming from in your system. So, as always, never stop practicing programming. It's always a very good mental exercise. Never stop reading code. And at this point as well, you should be ready to actually read some very basic C code. If we go into DSJS CLI, and we go into the source and look at main.c, and go down here, go into init configs, for instance, we can see here there's a very large amount. There are global variables, and there's actually a comment that says global calculated locations. We can see there's a static const here that can only be seen in this source file. We can see that there are static variables all over the place, and we can see down here, we can see variables that are just visible in this scope. Nothing else can see the variable tf or mfn outside of this function destroy module. This is a stack scoped variable, and we can see already two global variables here. You should be able to go through and look at some very basic C code and actually understand some of the basics of what the data management is actually doing. Other than that, you'll still probably be quite lost because of how C's functions and things work, but you should now at least be at home with the usage of variables, what exactly their purpose is, and how exactly they can be used. So, that concludes the episode. Thank you as always for watching, and see you in the next episode when we're going to be talking a little bit about I think we're going to talk about some very basic mathematics, how operators and expressions work, and then after that I'm planning on talking probably about how pointers, arrays, and strings work, because they're all effectively the same thing. So, see you in the next episode, and as always, never stop practicing programming.